Okay, so we're still working on group theory problem 1 from the January 2024 qual. And so we want to prove part C now. And so the proof of part C goes as follows. So we're going to recall by parts A and B that P is equal to 2 and Q is equal to 3. This is what we found in part B. And so because in part A we said that the number of Sylow P subgroups is Q and the number of Sylow Q subgroups is P squared, this means that the number of Sylow 2 subgroups, because P is equal to 2, is equal to 3, and that the number of Sylow 3 subgroups is equal to 2 squared, which is 4. And also, we should note that the size of G is equal to 24. So now we're going to take the Sylow 3 subgroups of G, and we're going to let G act on it by conjugation. And this has permutation representation phi from G into S4 because there's 4 Sylow 3 subgroups. And we're going to recall that by the first isomorphism theorem, G mod the kernel is isomorphic to the image of G, of phi, and this is a subgroup of S4. And also we want to recall that by Sylow's second theorem, the action of G on the Sylow 3 subgroups is transitive because each of the Sylow 3 subgroups are conjugate to each other. So this forces that the image of phi the size of the image has to be greater than 3. And so this means that the kernel of phi has to be less than or equal to 6, the size of the kernel. So we're going to fix a Q in the Sylow 3 subgroups of G. And we want to recall that the kernel of phi is a subgroup of the normalizer of Q in G. And so then by Sylow's third theorem, because the index of the normalizer of Q in G, the index of that in G is 4, this means that the size of the normalizer has size 6, has order 6. So once again, the kernel is a subgroup of it, and so this means that the size of the kernel has to divide 6. And hence the size of the kernel, its options, what it could possibly be is 1, 2, 3, or 6. So if the size of the kernel is 6, then this means that the normalizer is equal to the kernel, because the kernel is a subgroup, and they have the same size. And so this means that the normalizer of Q and G is normal, because it's the kernel, and this means that the normalizer of G in Q is equal to Q, and so hence Q is normal in G. And this can't occur because we've supposed that the Sylow 3 subgroups are not normal. So similarly, we're going to make a similar argument using the correspondence theorem for if the kernel is equal to 3. So if the size of the kernel is equal to 3, then we can observe that the kernel is normal in the normalizer because the index has index 2. So now, by the correspondence isomorphism theorem, because the quotient group of the normalizer is a subgroup of the quotient group of G, and because the size of G mod the kernel is equal to 8, so because the size of the G mod the kernel is 8, this means that G mod the kernel is a P group. And so this means that the normalizer of Q and G mod the kernel is a subgroup of a P group, which makes it normal. And so we have a similar situation. This is if and only if, by the correspondence theorem, this is if and only if, so the normalizer of Q and G mod the kernel is normal in G mod the kernel if and only if the normalizer of Q and G is normal in G. And so by a similar situation, this forces Q to be equal to the normalizer, and so Q is normal in G because it's equal to the normalizer, which also cannot happen because Q is a Sylow 3 subgroup and it can't be normal. So lastly, we want to consider when the kernel of phi is equal to 2, the size of the kernel is equal to 2. Well, then if we look at the index of the normalizer in G, by the correspondence theorem, we know that this actually is equal to the index of the normalizer mod the kernel in G mod the kernel, which is equal to 3. And because G mod the kernel is 12, this means that the size of the normalizer mod the kernel is equal to 4. But we said that the size of the normalizer is 6, and the size of the kernel is 2, and 6 divided by 2 is equal to 3, which is not 4. So the size of the kernel cannot be equal to 2. And hence, the only option left for the kernel is that it's equal to 1. And because the kernel is only has the identity in it, then that means that this is a faithful action, and so G is isomorphic to S4 by the first isomorphism theorem, which completes the proof. And so this completes the full problem for group theory problem 1 of January 2024.